So we're in the last legs here. 5 lectures left. I know, 5 episodes. It's kind of like the big countdown to the grand finale. And everybody's getting teary-eyed. Season 1's almost over. Okay, so we're moving on to finite elements now for the last bit of lectures here. And the way it's going to work is today, Friday, and Monday's lectures basically are going to sort of outline the theory, the setup, how to think about doing this stuff. And then Wednesday, Friday of next week, I will pop MATLAB up here, and I'll just walk you through demos, how to use finite element method, okay, with one specific toolbox, the PDE toolbox in MATLAB, because I have that. Okay, but really at the end of the day, it's going to be same buttons, just maybe different configuration for different packages. Okay, so but I think it's important for you to have the underlying idea of what goes on in these codes so that you can sort of be familiar with this. It's going to be a little bit of a change from what we've been doing. Okay, so let's talk about what's going to be involved here with finite elements. 1. Always an important step, discretizing the domain. This is what we've been doing, spectral methods, finite difference. And always in those, we pretty much just said, here's my domain, just chop it in equally spaced points. Or with Cheb, we did unequally spaced points, and there was a reason for that, to use these Chebyshev polynomials. But you'll see here, this is a little more complicated. Especially in 2D. Now remember, the only reason we're going down this road of finite elements is it's about boundaries. Okay? This is the one reason you go down this road, is if you have complicated domains, complicated boundary conditions, this is your tank. Okay? This thing can handle anything pretty much. Okay? So, discretizing the domains are one of the key steps here, and you'll see already in this discretization of the domain, it's kind of a complicated task. Okay, 2. Once you discretize the domain, we've got to pick how we want to represent the solution on this domain. So we're going to pick interpolating functions. So in other words, I'm going to break it up. The solution is known in a finite number of points. But ultimately, we may ask, I want the solution over the whole domain. How do I represent that? So you have to figure out, how do you want to give interpolated values? So you obviously have them at the boundary points. How do you do them elsewhere? Okay? So that will be important for us to decide. 3. Let's just leave it at that. We discretize, we build interpolating functions. What's the AX equal to B problem sitting in there? Remember, it's always going to come down to that. We spend a lot of time with AX equal to B because that's what MATLAB is all, that's what it's trained to do. Ultimately, that's what you're going to train your computer to do. Solve large matrix systems. If you've learned nothing else from this, from me, that's what you should walk home with. Hey, matrices. That's what I got to work with when I'm doing computing. Big ones. Okay? All right. 4. This is such a big issue that we're going to spend a lot of time about how to assemble these. You know? How do we actually go through then and build these? Not just say, what is this thing supposed to, what are they supposed to be, but then, geez, we've got to actually build them now. Okay? Finally, after you get all that, solving it. Good times. I know. You feeling it? You feeling the good times? It's like being in the summer. Okay. All right. All right, so I like to think this class is a little bit of sunshine in your life. I know that's not really true, but like I said, I like to think that. Okay, so don't break my groove. All right, so here's what we're going to cover today. We're going to talk about these two things specifically, and then Friday we're going to talk about these things right down here. Okay, so we're going to break it up into pieces. All right, the first thing about discretizing a domain is I'm going to not say much about it. I know. That kind of feels cheap, right? I know. You just kind of, but let me show you why. How does this thing discretize a domain? And that's one of the things that just this alone is actually quite a difficult task. So unfortunately, the little camera that's above there doesn't work anymore. But I want to just show you kind of what a picture of this might look like. There's a figure in there, and you say, well, I'm going to solve on this domain. But the nice thing about finite elements is, for instance, I might have structures in here. I might have, this is part of my domain. And suppose I have something embedded in my computational domain with this kind of really awkward shape, for instance. Okay? And what does the discretization do? Now, normally what we've done with discretization is we've just chopped it up this way, chopped it up this way. Okay? You could do that. If you're doing finite difference, you could just chop away. And then you say, well, you know what happens when I get in here? Well, here's my grid. And then you'd say, well, I can only have solutions at grid points. Right? So here's my boundary. I'm not on a grid point, so I have to like pick the nearest thing to it, right? So you start seeing how crappy a job this is going to do in representing this domain, right? So you have this complicated domain immersed in this thing, and you want to say, well, if I chop this up, it's going to be bad. There's two options to this. I could just keep cutting it finer and finer and finer. Right? Make smaller dx's, smaller dy's. And what is that going to cost you? A lot of your life. Okay? Why? Because you have to sit and hit run. But our whole point is to take big dt's and as big as delta x's and delta y's that we can get away with. And this is just forcing you to say, if you go with this philosophy of finite differencing this thing, it will ruin your life forever. Okay, not quite that bad. But anyway, it's a bad approach, ultimately. By the way, what about spectral methods? I have this boundary sitting inside of there. What do spectral methods do? They actually expand in global functions that fit on the whole domain. Does the cosine know that there's this giant thing sitting in the middle there? No. That's a problem. Spectral says, hey, I'll just take functions that live on the whole thing. And you say, well, wait a minute, there's a problem. I have this thing right in the middle. Okay. So both finite difference, spectral, suck. I don't know what I had here. Okay, drawing one. So here's what finite element does. It says, give me your poor and weary boundaries. It's kind of almost is that a quote? I think it is. It's from Constitution or something. No. Yeah, it's the Statue of Liberty. I knew it was something American. Okay. And what I'm going to do with this, I'm going to get you your thing, and I'm going to basically say, I see your boundary. I see it. And what I'm going to do is I'm just going to take it exactly as it is, and I'm going to start drawing triangles on it. Looks like Chinese checkers, doesn't it? Okay. Sort of is. You just basically start saying, look, I'm just going to start drawing triangles all over the place. And I'm just going to make a domain made up of triangles. All the way out to the boundary. By the way, out at the boundary, not much is going on, so I might be able to take really big triangles as long as I connect them right to triangles in here. That's the idea behind finite element. Give me your really complicated boundary, interior, whatever you want to do, and what I'll do is, first, I will essentially, whatever your boundary happens to be, right, whatever happens to be there, suppose I have a boundary like this, that's what it's supposed to be. What I'll do first is I will just basically fit a bunch of points on it. and then I'll just start drawing triangles off that point. So in other words, the first thing I do is try to match your boundary. I don't try to make your boundary fit within my grid. I just make my points fit on your boundary and then draw my grid after it. Okay? So this discretization process here, you might start drawing triangles off here, and you can see that, you know, and then you start building yourself a grid of points. Wherever those triangles intersect, this is one of your points of solutions. U, X, I, Y, I. Okay? Finite element takes a very different view, then, of everything. It just says, give me the stuff, I'll draw triangles. Triangles not the only option, by the way. We'll talk about others. And I will represent now the solution on this big structure here. And by the way, generating this is in itself a fairly complicated mathematical exercise. Okay? A couple things about these triangles. And this is why we're not going to talk about it. This is why you go to a commercial package and you put in your domain and say, go, and it gives it to you. Someone else wrote a nice little algorithm for you to give you all these triangles. Okay? If you're doing research in finite elements, write your own triangles if you want. If you're not, this is a lot of work for you. If your ultimate goal is to actually solve the problem, that's what you're really interested in, it's going to cost you more time just to get that triangle grid, write a code for that, than anything else, right? So it's just use it. Even if you were to take this problem and just say, go ahead, I got my boundaries, triangularize it, now I'm going to take out the grid, and then I can do stuff with it as I want. But there's some really nice algorithms out there. And we'll play around that in the code. Now, a couple things about the triangles. Width and height should be similar. Okay? No Kareem Abdul-Jabbar triangles. No Fat Albert triangles. They don't have to be equal, but roughly speaking, the triangles should look fairly, width and height should be somewhat similar. Okay?
Give a triangle, right?
Yeah, for every given triangle. By the way, the triangles can change in size. So, in fact, this is a very nice thing. One of the things that's nice about triangularizing a grid is wherever you have a lot of structure, and we'll see this actually as we do this implementation in class, it oftentimes puts a lot more triangles near complex shape structures. And in fact, that's kind of what you need, right? Near where you have a lot of stuff happening in corners and edges, you'd want more grid points. Whereas way at this edge, where not much is going on, you might have big triangles. And you'll see when we build the code, you can just basically refine this mesh as much as you want. Okay? So it automatically does things like that. All right. All shapes, okay, in the computational domain should be approximated by polygons. All shapes are. So when you start looking at any shape in here, you want to start thinking about, okay, I can have a very high degree polygon, but the point is that ultimately, whatever shape I pick in here, this shape is going to be a connect the dots. So we're never going to get that far away from connect the dots, right? So I have a complicated shape, just a matter of how many points you want to put on connect the dots. Okay? Finally, my biggest advice to you, use a commercial package. This is so unacademic advice, right? Normally, they'd say up here, well, just for your good of your education, you should write your own. It's like, yeah, I'm not writing my own. I'm telling you that right now. Okay. If your advisor asks, like, what did he say? Just say, oh, no, he says we should write our own just, on our free time over Christmas break. That'll make them happy. Oh, okay. That's good academic advice. All right.